So we'll continue our discussion on semiconductor laser diodes. And so last time we looked at sort of the DC characteristics, right? The optical power versus injected current, and we saw this threshold kind of behavior. Right? And we also saw how lasers are much more efficient at converting the electrical power into output optical power compared to, let's say, LEDs. So of course, for communication, right, one important metric, another important metric is that how fast can we modulate these laser diodes, right? How efficiently can we transfer the electronic data on optical fibers, right? And how fast can we do this, right? So for example, for LEDs, we saw that the modulation bandwidths were roughly like maybe below 200 megahertz, right? So for direct current modulation, and so you can't really go to very high data rates with LEDs. So we'll see what that looks like for lasers. Right, so we are talking about, of course, direct current modulation. Right, so sometimes when laser diodes are operated like this, they are also known as DMLs, or directly modulated lasers, right? Where basically we modulate the current, injected current itself. We have some DC current and some time varying AC component, right? And then the optical power coming out also has this data printed on it, right? So again, if we recall our DC characteristics that we had derived, right? So optical power versus injected current. So it looked like this. So there was almost nothing up to this threshold current, right? And then beyond that, sort of like the power increased linearly, right? So imagine that, let's say, we have a DC current which is above the threshold. So this is known as the bias current. Okay. So, and then on top of that, we impose a AC signal, right? So let's say we have a sinusoidal signal of some particular frequency over this bias signal here, right? Of amplitude Im and frequency omega m, right? So that means that the total current as a function of time is a DC component, IB, bias current, plus a modulation current, right, at frequency omega m and amplitude Im. So, okay. And so basically, I mean, just from these characteristics, you can see as I vary the current, the optical power emitted is also varying, right? So about a DC power PB and then with an amplitude PM, right? And we want to see that basically as we vary this frequency omega n and take it to higher and higher values, how does this optical power respond? So, I mean, if you recall, basically we did something similar for LEDs, right? So there we had a simple, just one equation for sort of this carrier dynamics, right? And that basically determined the entire properties of the system. And so we basically took this type of time varying current and saw how the carriers responded and basically got the modulation response like that, which was basically primarily determined by only one constant, which was the carrier lifetime, right? So here, of course, the situation is a little bit more complicated, right? So as you know, we have two equations now, right? One for the carriers, right, and one for the number of photons in the laser cavity. And both of them are coupled to each other by this term G, right, which actually just also depends on the number of carriers. Right? So if you put this G here, you can see here there's a term NC times N photon, and similarly here there's a term NC times N photon, right? So there's a coupling between the carriers and photons. Okay, so you can see in response to this time varying current, there will be a time varying carrier concentration or number of carriers in the active region, and also a time varying photon number, right? So since these are sort of linear differential equations here, we can assume that the carrier concentration and the photon number also respond at the same frequency as the drive. Right? That's also another way of saying that this response here is completely linear. Okay. But you can include some extra effects to model the laser more realistically, in which case this won't be perfectly linear, right? There will be some nonlinearity to it. And in that case, basically the response will again be nonlinear, which means that there might be different frequencies in the so the carriers and the photons might respond at slightly different frequencies also, not present in your drive. But let's not go into those complications for now. So let's assume this response is perfectly linear. Okay, so basically the carrier concentration again has a DC response, right, plus a time varying response at the same frequency as the drive frequency. Similarly for the photon number. Okay. And see, oh sorry, there's a mistake here. Thanks for pointing that out. Yeah, this is top C, right? Of course. Yeah, right. So now we have two variables here. So basically, you can plug these solutions into these equations, right? And then compare the DC terms on both sides and the time varying terms on both sides, right? Just like we did for the LED, except we had only one equation there. Now we have two equations. So we have two unknowns to sort of solve for, right? This NCM and M photon. But the procedure is the same straightforward. So another thing to point out here is we also noticed in the LED case that so these this NCM and NPHM will in general be complex numbers, as we'll see, right? So what does that mean? Of course, the number of carriers or the number of photons has to be a real number, right? But that just means that, so if we take that as, so if you take this as a magnitude times a phase, okay, so basically we can include the phase with this omega mt, and basically then we'll see that, so okay, so the carrier concentration is varying by this amount, but it's the time variation is out of phase with my drive. Okay? So that's just the complex number just tells you that the response is slightly out of phase with the drive current. So for example, if I plot with respect to time, so if my current looks like that, then let's say the carrier concentration looks slightly out of phase, or similarly, let's say the the photon number is slightly out of place. Okay, so for example, so recalling the LED case also, we got, so for this NCT, when we saw this was a complex number, right? So the response we got was a complex number, we just indicated the phase difference. Right. So anyway, so the procedure is the same. You just substitute these into these equations. Now you'll have two equations, right? So and then you equate the DC terms on both sides for both equations and also time varying parts. So you can get from the DC terms, you will get this NCB and N photon B, and from the time varying terms, you will get NCM and N photon M. Okay. So you can just go ahead and do that. So if I look at the AC amplitude of the photon number, it will go something like this. Okay, so yeah, just do this at home and verify that you get an expression like this. Okay. So where this N photon B is the DC photon number, right? Which is related to the current DC part of the current IB. So what we had derived last time for the DC response, right? So this will just depend on the IB bias current here. Same expression that we derived last time, right? And of course, so you can see that the AC term depends on the amplitude of the AC current here, right? And then you have a term in the denominator. So for the LED, we had a term something just like this omega plus I gamma, right? Something like that we had in the denominator. But here now it's a little bit more complicated. We have two terms, and we also have this additional omega R here with omega. Okay. So what is this omega R? Okay, so when you have the solution, you can check that this omega R comes out to be that. Okay, so it depends on again the DC photon number, which depends on the DC current. Right, these are constants here. Gn is a constant, the material constant we discussed last time, and this capital G again depends on. So this capital G will basically depend on the DC carrier concentration. So when we put that DC carrier concentration here, we get G. Okay. So okay, so you can see that the response is of course more complicated, and there's this another constant here, gamma R, which is coming here also. Okay, so this gamma R. Okay, so this omega R, so FR is known as the relaxation oscillation frequency. Okay, so you can see it's a property of the device, right? So you can see it just depends on the device constants and the bias current. Okay, so we can also simplify this a little bit more. Maybe let's just define this gamma R first. So this gamma R is given by that. Again, depends just on constants and the DC photon number, which depends on the bias current. Okay, so this is that. I mean, you can see from here, this is the damping rate of the relaxation oscillations. Okay, so what is this relaxation oscillation frequency, right? You can see this is, I mean, it has units of frequency. This is some natural frequency which is coming out based on the device parameters and where you bias it. Okay, so it's something like a natural frequency at which the device responds. Okay, so something like you have a pendulum, depending on its length and tension and mass and whatnot. There's a natural frequency of vibration, right? And the response of the pendulum when you drive it with some particular frequency, you know that the response peaks at its natural frequency, right? So you know a simple harmonic oscillator, right? So it has a natural frequency, and as you vary the drive frequency, the response or the amplitude that you for a given drive, the amplitude of vibration that you get peaks at this natural frequency, and then it falls away from the natural frequency. So it's a property of intrinsic property of the device. So similarly here, there is a natural frequency which is called the relaxation oscillation frequency, which is basically a characteristic frequency for these laser diodes. Okay, and why this is happening is basically because we have these dynamics between the carriers and the photons, which are coupled to each other, right? So what is happening is fundamentally that, so let's say the number of carriers in the active region increases slightly. Okay, so you can imagine that increases the recombination rate and it produces more photons. Okay, so now the photon number increases. Okay, let's say lagging behind the carrier by some small delay. Then as the photon number increases, right, it's causing stimulated emission, right, which means it's causing carriers to recombine, right? So this increase in the photon number feeds back and decreases the carrier concentration, right? So you can imagine that. So what's happening is, so let's say first the carrier concentration increases, following that the photon number increases, right? But now this increase in the photon number causes the carrier concentration to drop, right? Which causes the photon number to drop again, right? But when the photon number drops, the stimulated emission rate goes down, and basically now you have the rate of injected carriers are not being recombined, so now the carriers start back up again, and then this photon numbers, right? So you have these oscillations that can go on because of these coupled dynamics between the carriers and the photons, right? And the characteristic frequency at which these oscillations are happening is basically given by this relaxation oscillation. Okay, so you can simplify this expression a little bit more to see what this frequency depends on. Okay, so first thing is that typically this first term, right, is much larger than the second term. Okay, so I can sort of approximate omega quite well like that. Okay, and so you can see that it's scaling as the square root of the photon number, right, or basically square root of the bias current or square root of the optical power emitted, right, from this. So square root of the DC power being emitted. Okay, so you know that. So obviously we're operating above threshold, and you know that above threshold, right, this G is basically just 1 over tau photon, right? Gain is equal to loss. right? So in other words, this NCB is actually just the threshold carrier concentration, right? Because we know that anywhere above threshold, we saw that the carrier number gets clamped, right, at the threshold. Anyway, right? So we can just replace G by 1 over the photon lifetime here. Okay, and then if we use the linear relationship between the optical power and the current. So from the equation we derived last time, so this photon number, the DC photon number depends on the bias current, like that, right? So IB minus I threshold. Right, so this is basically, so the photon number, the DC photon number is just tau photon by Q times IB minus I threshold, right? This linear relationship. So from here now you can see directly that basically this relaxation oscillation frequency depends on basically the bias current, or how far the bias current is above the threshold current, right? And then this Gn, which is a constant, right, of the material. You can also write this in a slightly different form to see sort of the time scale, right? So from here, again, this is a frequency, so it's not clear from here sort of what will be the magnitude of this frequency. Of course, it depends on the bias current, but to more clearly see like what is the time scale which decides this frequency. Right, so recall again from last time we had this expression for the threshold current. Right, basically we derive this from this condition, right? Basically from this condition, and that G is equal to Gn times Nc minus N naught, we derive this equation for the threshold current. Right, and typically again, so if your bias current is sufficiently above threshold, then this second term, okay, I mean these are all constants of the device anyway. So typically if you take any typical laser diode with typical parameters, this second term is typically much bigger than this first term. Okay. So what we are saying is this is roughly okay. So typically the second term is much bigger than this first term, right? So this, remember, is the number of carriers required to reach transparency, or just the population inversion threshold, right? And this is basically decided by the losses in your cavity, right? Tau photon is basically given by that. So typically the second term is much bigger than the first. Okay. So basically I can approximate Tau threshold like that, or in other words, if I write this, so let's take some terms there. So Gn I threshold over Q is basically 1 over the product of the carrier and the photon lifetime. Okay, so here if I write this as, so I take I threshold out common from there, so I'll get Gn I threshold over Q square root, and then IB by I threshold minus 1 square, right? So I've just taken I threshold common out from here, right? So if I do that, you can see that, and then I replace for this quantity 1 over tau c times tau photon. I'm doing all that. Basically, you get this relaxation oscillation frequency to be, so it depends on how far above threshold you are biased, right? But then the time scale sort of is decided by, fundamentally by the product of this carrier lifetime and the photon lifetime. Okay, so you can see that basically it's the interplay of the carrier and the photon dynamics, and sort of like the geometric mean of the lifetimes is giving you this frequency of oscillation. Okay, and the frequency increases as you go further and further beyond threshold. So the device responds faster and faster. But it's not very strong, like the dependence is square root. Okay, so again to get the frequency response, so typically this this number, so again recall that this carrier lifetime was in the few nanoseconds, let's say between 2 and 5 nanoseconds. Photon lifetime was roughly in the few picoseconds, between 1 and 10 picoseconds. Right? So this number typically comes out in the few gigahertz range. Okay, so that's the characteristic frequency we are talking about. Or FR is in the few gigahertz range. Okay, so now we can define, so we have this AC part of the photon number, right? And then this, I just erased it. So the AC part optical power is again just proportional to this time varying photon, right? Just like the DC part, we calculated the number of photons in the laser cavity, and then we multiplied by some constants depending on the sort of mirror reflectivity, etc., to get the power coming out. Same case here, we multiply by the same constants to get the AC power coming out, right? But anyway, so it's proportional to this. So I can define a transfer function, right? Just like we did for the LED case, where right, so I calculate the magnitude of this at some frequency omega divided by the DC. Term. Okay, for the same IM, of course, right? So basically, I'm just varying omega m, right? And so I put omega m equal to omega m equal to 0. So you get this. And if I take the magnitude, because again this is a complex number, Okay, so that's the transfer function here. I hope this is visible, yeah. Okay, so again, it looks a little bit more complicated than the LED case, where we just had like a Lorentzian, like something like 1 over omega square plus gamma square. So again, typically, this omega r is much bigger than this gamma r, right? So omega r we saw is like few gigahertz range. Gamma r typically is, let's say, megahertz. So typically this term is much bigger than this term. Okay, so sometimes this is also approximated as, so here also if we neglect gamma r compared to omega r, you can approximate this as, so if you neglect gamma r here, so you just get okay. So this half goes away because there was square here. Right, and of course, so this h of omega has to be unitless. It's a transfer function. So you can see if you have omega square here, it should be omega square also. Okay. So basically the transfer function somewhat looks like that. Okay, so if you plot this as a function of omega, like here. Okay, so here we have the modulation frequency f, which is omega over 2 pi in gigahertz. And I'm plotting its transfer function magnitude in dB. So 0 means 1, 0 dB means unity, right? Minus 6. Okay, so 6 dB means h omega to the 4. Right, so now this transfer function, so this omega r again, recall, depends on the bias current, right? So basically, for a particular bias current, I'll get a particular curve. Right, so as I change bias currents, I'll get different curves. So for example, okay, so these are different for different, right? So basically, you can see the transfer function first peaks, okay, and this peaking is happening basically at this relaxation oscillation frequency. Okay, so this peak occurs at basically sort of at FR. Okay, so you can see that as so these are for different bias currents here. This is IB 1.6 times threshold current. This is 3.1 times threshold current. Okay, this is 6 times. Okay, you can go further, of course. So this is. Okay, so as you are increasing the bias current, this omega r is increasing, right? So this peak is sort of shifting to higher frequencies. Okay, and basically in effect the bandwidth. So if I compute the bandwidth as the point at which this goes down to this goes down by 3 dB, right? So the bandwidth is increasing for increasing bias current. Okay, so basically the result is that if you want higher modulation frequencies, you have to bias it at a higher DC current. Right. So of course, this is recall for sort of what is known as small signal modulation, right? So basically, what we sort of assumed here was that the variation in the current, right? So this is IB and IM, right? So IM is much smaller than IB, right? So it's what is known as small signal modulation. You have a bias point and then you are varying a small amount of outcome, right? So this kind of response is sort of more useful, for example, in when you're doing analog modulation. Right? So you have some DC bias point, and then about that you're putting some RF signal whose amplitude is smaller than the DC, much smaller than the DC component, right? And then so these are useful for like radio over fiber links or what are known as microphotonic links, etc. And you can see that you can basically, as you increase the bias current, you can go to pretty high frequencies, right? Beyond even 10 gigahertz. Okay. So what is plotted here is this complete expression. You can see that for this approximate expression at omega equal to omega r, this actually blows up to infinity, right? So in this approximate expression, this is actually going up to infinity, and then again coming down. Right, so this approximate expression doesn't work well at omega equal to omega r. So there you have to use the complete expression to get this finite peak. But this works well away from the peak, like either here or. Okay, so we can calculate the so this bandwidth of operation by saying basically at what point, so this omega 3 dB, right, this becomes half. So again, that's what is known as the optical 3 dB. So this is 2 pi f 3 dB. So this is the optical 3 dB modulation bandwidth, just like for the LED case, right? You can also define like an electrical bandwidth if you put this equal to 1 by square root of 2. But anyway, so if you do that, you can see that happens for so this is F3 dB comes out. I mean, if you just use this approximate expression, it's straightforward to see that this comes out to be √3 times the relaxation oscillation frequency. Okay, so here we've used again this approximation that omega r is much. Okay, so again, so the 3 dB modulation bandwidth scales with the relaxation oscillation frequency, which scales with the bias current, right? So if you want to modulate, if you want to send signals with higher bandwidth or higher frequencies present in the signal, then basically you want to bias it at higher currents. So typically, like if you look at sort of modern DFB lasers which are used for telecom, you can sort of get to about 20-30 gigahertz of modulation bandwidth, sort of at bias currents about 10 times the threshold current. Okay. So you can see that easily you can sell analog signals with that kind of bandwidth by using directly modulated lasers, directly current modulated lasers. Okay, and again compare this to LED case where we were talking about like 200 megahertz. So, right, this is 2 orders of magnitude higher as compared to LEDs. So last time we saw that lasers give you about like 2 orders of magnitude or more higher power, optical power, and also they give you 2 orders of magnitude or higher modulation bandwidths. Okay, so that's as far as sort of like the analog modulation or small signal response is concerned. Any questions on this? What is a little bit more relevant for sort of optical fiber communication links, especially you know that nowadays we operate with for especially telecom links. We're talking about digital signals, right? So ultimately we are talking about transmitting bits or high or low signals, right? So basically you want to send a pulse. So in the simplest scheme of modulation, we want to send a pulse having some high power for bit 1, and then sort of like turn the laser off and send no power or very low power for bit 0, right? So that would be what is known as large signal modulation or digital modulation, where you are turning the laser on and off, right? So in this case, we are operating about a bias point and then changing very small amount about that. But for digital modulation, of course, you're talking about like on and then off, on and off, right? So you're going almost like below threshold, above threshold, right? So that is known as large signal modulation. So with that, of course, you cannot go to such high speeds of like 20-30 gigahertz, right? So let's just look at the large signal modulation. Okay. Okay, so in that case, basically what I want to do is sort of like go between two states. So bit 0 is some current I naught, which is below threshold, so that the device is off, right? There is no optical power coming out. So this is like the power coming out for bit 0 is almost 0. And then I go to I1, which is above threshold, right? And that is giving me a power P1 for bit 1, which is, of course, a finite value, much higher than, right? So you can imagine basically what I'm, so if I look at the current, I'm sending sort of square pulses here with some bit period, right? Let's say some bit period TB, right? And let's say bit 0, I'm sending I0, right here. And then for bit 1, I'm sending I1, current in the device, and then the threshold current is somewhere in between here. Right, so basically you are saying that, okay, so it's off here, and then on here, or off here, on here. So this would be simplest, like for example, OK, on-off keying modulation. Okay, so basically the ideal case, what I want is that the optical power should also sort of go like this between P1 and P0, right? And P0 is basically, you can see that P0 is almost 0. Right, or like in the limit when we neglect spontaneous emission, it's actually identically 0. right? So basically we want this to happen, but of course, again you have this complicated dynamic between the carriers and the photons, right? So you can imagine that the device is off here, and then the device will have some finite response time. Okay, so it won't. So if you change your current suddenly, the device won't immediately respond. Okay, so there will be. So this is an ideal case. So for very low data rates, right, you can sort of have this kind of response. But as you increase or decrease this bit period here, go to higher data rates, then this response time, okay, the rise time of this laser cavity, or basically the rate at which the photons and carriers are building up, will start to matter. Okay, so if I actually, so let's say if I'm looking at some very high data rates, so now this doesn't look vertical on this time scale. What you actually see is sort of a manifestation of this relaxation oscillation that I was talking about, right? So imagine what is happening again in the device, right? As soon as you increase this current here, you're injecting a lot of carriers suddenly into your device, right? And so immediately what happens is that again those carriers, sort of a fraction of those recombine, generate some photons, right? So the photon number also starts increasing with some lag. But now again these photon numbers, these high photon numbers start causing their own stimulated emission, and this stimulated emission causes recombination of the carriers, which again decreases the carriers after a certain time again, right? Basically this relaxation oscillation that I was talking about. So again, if you know from your for example, some basic linear systems theory, right? So if you have any system which has a linear finite bandwidth response, right? You give a step function to it, it doesn't respond. The output is not a step function if it has some finite response time or a finite bandwidth, right? What you see is sort of this damped oscillations. Okay. So there is some rise time here. Okay, so there is some time delay for the optical power to reach this high value, which corresponds to bit 1. And not only that, not only is there a delay, there is also these oscillations, which are basically this relaxation oscillations happening. So this response is basically like a damped sinusoid, which happens in any. So again, recall that basically we sort of effectively modeled this system like a simple harmonic oscillator, right? It has a natural frequency and it has some damping rate. So for any such system, when you apply a step function, you get this damped sinusoid response. Okay, so one can estimate, right? So basically, again, what is happening is that the carrier and the photon number are coupled to each other, and they take some time to build up, and then they also undergo these oscillations because they're coupled to each other. So this delay time. Okay, so again, like we can start from those equations for the carrier and photon number dynamics. And now instead of a sinusoidal response, you can apply like a step response and then try to see the, just for like any linear system. Okay, so you can estimate what this time delay will be. So this rise here is sort of like an exponential rise. So as I said, this is like a damped exponential. So this rise is sort of like a exponential rise. Okay, so in some sense you can think about it like this. So you have these. So if you have this equation for the carrier dynamics. So let's say we start from below threshold, right? So I naught is below threshold, so the device is off. There are no photons in the cavity, right? So this other than stimulated emission term is 0. So you have this equation for the carrier lifetime, and now you put this I of t as a step function going from I0 to I1, right? So now your NC will start from some low value here, which corresponds to the number of carriers for I naught, right? And then it will start rising. And you can see this is a linear differential equation with some time constant tau c, so it will start rising like this, and then eventually reach what is known as the threshold number of carriers, right? At which point the device turns on, right? So basically, this tau d is sort of this time that the carriers takes to start from this NC0 value for I0 to reach up to the threshold value. Okay, so this rise here, we are saying it goes something like sort of. So this NC of t is going something like NC0 plus NC threshold into or NC0 1 minus e to the minus t over td, right? So it's like an exponential rise. Anyway, so if you calculate what time it takes, so this is not td, so this is some time constant tau here, or actually it will just be tau c, right? And you just calculate at what point. So this one. Yeah, anyway, so this will go something like, right, where this delta will depend on the current step I1 minus I0, and you calculate at what point it reaches this threshold value. Right, so at t equal to td, it will reach this threshold value and the device will turn on. So to do that, this td comes out to be, so of course it depends on the carrier lifetime, and it depends on the current step that you give, I1, the difference of I1 and I0. So the dependence is something like this, log of, because again you have an exponential rise here, so if you calculate the time, that depends on the log of the current. Okay. So this delay time or the turn on time, of course, is proportional to the carrier lifetime, and then log of this ratio. Basically, it depends on the current step that you give, I1 minus I0 divided by how far I1 is. Okay. So again, recall I naught is less than I threshold, right? Which means that, so this number is of course bigger than 1, so this number is a positive quantity. So this expression works when you start from off state, so when I0 is below I threshold, and then you turn it on. Yeah, so I mean, I said that, so in this equation, right, you just put, so I of t will be something like I naught plus delta I, which this will be like I1 minus I0, u of t, right? Step function, and then so you solve for NC of t, you will see that because so you have this NC over tau c term, right? So the NCT will go as some NC0, which corresponds to I0, and then plus some delta n, which will be proportional to this delta I, times this exponential rise that you get, e over 1 minus e to the minus t over tau. Right, so this is just a linear differential equation with some time constant, right? So for example, if you have an RC circuit or something that has the same kind of equation here, right? Like the charge on the capacitor, voltage across the resistor, it varies similarly, right? So you can see this like the resistive term and the this tau will give me the RC, right? So it's just like any system with a first order system, right? So you know that when you apply a step function, you get something, a response like this. Right? So if you have an RC circuit, you close the switch, the charge builds up across the capacitor or the voltage like that, right? So exactly the same you get here. And now I just calculate at which point this becomes equal to the threshold value. Right? So at t equal to Td, NC becomes NC threshold. So that gives me my turn on time. Okay, so using this, you can get this turn on time, which depends on the carrier lifetime and the this magnitude of the current. Okay, so you can see that if you want to minimize the turn on time, you want to minimize this quantity. So this is a constant, right? This it's a material constant. You can't do anything about it. So this is typically like a couple of nanoseconds or so we discussed. And then this one is under your control. So now you can see. So basically, you want to minimize this. So the lowest value of this can be is 0 when this argument inside the log is 1, right? So when I naught is equal to I threshold, that's the minimum value. And that in that case, so basically we're saying that if this I naught is equal to the threshold value, then basically you get 0. So of course, this expression doesn't work in that limit, right? Our assumption was that the device is off. We neglected this term, right? So our assumption is that the device is off. So I naught is less than I threshold. But as you can see that if you want to minimize the turn on time, I want to make I naught as close to I threshold as possible. So I want to be off, but just off, not too much off. Right? I just want to be just below I threshold for this to be small. So and this expression doesn't work once I get to I threshold and beyond, right? Because our assumption in deriving this was that I'm going from off to on state. But anyway, yeah. So basically, for example, you want to operate at I naught equal to 0.9 times I threshold for the bit 0, right? And bit 1 can be like 2 or 3 times threshold or even higher. Right? So that's where you want to operate for fast response time. So there's a question, can you bring out the physical significance of I0? What do you mean? This is just the current that I'm sending. I mean this is just the current I'm sending into the laser for bit 0. Right? So I'm sending some current here into the laser device and giving me some optical output power. And so I'm so I have some electronic data in digital form. So low current corresponds to bit 0 and high current corresponds to bit 1. So naively you would think that okay, maybe I0 can just be 0, right? I don't send any current for bit 0. You can do that, right? I0 can be 0 also. In that case, you can see that the rise time will be quite slow. You can put I0 equal to 0 here. Right? Or if I0 is 0, you basically want I1 to be much higher than I threshold, right? To make this small. And typically you can't go very, very beyond I threshold. Like maybe you can go 5 times. Certainly not, you probably want to say below 10 times threshold current to not damage the device in the long run. And so you can't make I1 very large. Probably 5 times or 7 times I threshold is the maximum you can go for I1. Okay. So yeah, I1 and I0 is just the currents that you're sending for bit 0 and bit 1. Okay, so basically in the end, what we are saying is that, so if you want to operate at high bit rates, you want I0 to be close to I threshold, right? To make this small and so this TD is small. Right, so of course you can see that your bit rate cannot be, so roughly you want it to be twice or maybe 4 times TD, right? So if you also want to turn it off, so if you want to see a nice pulse here, then this bit period has to be, let's say, a few times this turn-on time or delay. Okay, and similar dynamics also happen when you turn it off. So not only this rise time, right? Once the carriers rise, then also the photon number rises, and then we have this feedback between the photon and the carrier number, and you get these oscillations. Okay, so for that now you need to include this next term also. So then now it becomes more complicated, but yeah, you can numerically solve that and get this response. Okay, so how small, how fast can you make this? So like in the limit, when I set I0 equal to the I threshold, you can see that maybe I can make this really small. Okay, but there's a lower limit to this. I can't make this as small as possible, and the lower limit is coming again from these relaxation oscillations, right? So basically, not only do you have this rise time, but you also have these oscillations going on, and you can imagine that you cannot go faster than these oscillation cycles. Okay, so the fastest sort of you can do is like 1 over the relaxation oscillation frequency, okay? Because you cannot beat. The system will respond at its natural frequency, and you cannot go faster than that, even if you make this very close. So the lower limit is typically given by this, and we can see here that depends again on sort of the product of the carrier lifetime and the photon lifetime. And IB you can sort of roughly imagine here to be like sort of, let's say, midway between I1 and I0 or something. So this factor typically will be, and it's a square root here, so if you have, let's say, 5 times I threshold is square root of that, so this number is close to unity, maybe 2 or something. So basically, roughly the maximum you can get is sort of like 1 over, or the time period you can get is the square root of. Okay, so the fastest sort of response you can get is this, the geometric mean of the carrier and the photon. And again, if you put these numbers here, right, typically this comes out to be like, let's say, 100 picosecond. So again, tau c is in nanosecond, this is picosecond. So you take the geometric mean, you get about 100 picoseconds. Okay, so basically that means that the bit rates we are talking about here are typically less than 10 gigabit per second, right? Because it has to be greater than this turn on or turn off time. So for digital modulation, typically we are restricted to less than 10 gigabit per second, right? So for analog modulation, we saw we could go up to maybe up to 30 gigahertz, but for digital modulation, typically we are restricted to like 10 gigabit per second. Okay. Because here we're talking about large signal modulation, right? Sort of going from off to state and back. Whereas here the laser was always on and we were making some small changes around. Okay, so I hope that's clear. Any questions on this? Okay, so in addition, right, so we can make pulses by directly modulating the laser current up to sort of 10 gigabit per second speed. If you want to go beyond this, then we have to use what is known as external modulation, right? An external electro-optic modulator which is outside the laser. So we'll briefly discuss that also after this. But these electro-optic modulators, probably you studied about them in your optical electronics course, for example. So with those external modulators, you can go up to higher speeds, like maybe even up to 100 gigabit per second. So in addition to, of course, so you can make pulses, so that's very nice. But there's an additional effect which happens when you do direct current modulation with these lasers, and that is you get a frequency chirp. Okay, so these pulses are actually not so-called transform limited pulses, right? The pulses that you get also have some chirp on them, and that fundamentally is also coming because so when you are sending current into the device, right? So you're sending carriers, electron hole pairs into your active region, and the refractive index, right, actually depends on the carrier concentration. So when you're changing the number of carriers, you're actually changing the refractive index of this medium slightly. Okay, and basically you know that you're forming some sort of like a mode in the laser cavity here, right? And you can imagine what that is doing is sort of changing the effective index or the phase acquired by this mode traveling across the cavity, right? And so now if you have a time dependent current, the refractive index becomes time dependent, and so the phase acquired becomes time dependent. And a time dependent phase is basically frequency, right? So that's how you get this frequency chirp. So because the refractive index depends on the carrier concentration, and the carrier concentration is now a time varying dynamic quantity. Your phase and equality now frequency becomes a time dependent quantity. Okay, so if you look at sort of the phase acquired by this optical field inside the laser cavity, okay, it sort of goes something like this. So it depends on the carrier concentration here, N of t. Okay, and this beta c is basically sort of it's giving you some magnitude by which the phase is changing for a given amount of change in the carrier concentration, and this beta sub c is known as the line width enhancement factor. Okay, so we'll see that so this beta c of course determines the amount of frequency chirp on your pulse, and it also determines, we'll see, sort of the line width of the laser. Okay, so it's called line width enhancement factor. Okay, so typically for the semiconductor laser diodes, so for if you look at InGaAs P devices, typically this beta c is in the range between, let's say, 2 to 8. Okay. So, and it sort of depends on the size of the active region. Okay, so if you have a bigger active region, then you can imagine this effect will be worse, right? Because you have more number of carriers and it will change the refractive index more. But if you have a smaller active region, then this effect is smaller. Okay. So if you make the active region really, really thin, so we discussed this briefly, so go into sort of this quantum well regime, like below sort of, if you go to the scale of tens of nanometers of thickness, then basically you can make this effect really small. Okay, so for so-called multiple quantum well lasers, where basically the active region is not, so for the standard devices, right, the active region we saw was typically like 100 to 100 nanometers thick. For these multiple quantum well devices, basically you have very thin layers of this active region, each of which, right, so that's why it's called multiple quantum wells. Each of them is like a very thin layer of, let's say, 5 to 10 nanometers or something like that. and you have multiple layers of this. So that on the whole constitutes some active region. With these multiple quantum well lasers, you can reduce this to sort of around 1. So that reduces the chirp that you get on your pulses. Recall again our discussion on dispersion. If you have a chirp pulse, and if the chirp sign is sort of the same sign of chirp as the dispersion in the fiber introduces, then your pulse will broaden even faster. So this chirp is actually important for long haul links. So from this phase, if you calculate the frequency shift on your pulse, right? So that will just be the derivative of the phase, right? Okay, so that will be already this expression is the derivative of the phase, so it's just that. So it's just this divided by 2 pi. Okay. So you can see that it's going as the carrier concentration, or roughly it's going as the optical power, right? Basically, so this this time varying carrier concentration is giving me a time varying optical power, right? And that is what is basically modifying my phase. Okay. So actually, if you look at the frequency shift, that sort of just follows my optical pulse. Okay. So again, if I look at optical power here, so let's say that goes like this. So we put some numbers here. Okay, so this is the optical power in milliwatt. Coming out of the laser. On the x-axis is time. So this is my current pulse. Okay, so this is time in nanosecond. Okay, so I'm giving a current pulse here, which is half a nanosecond in duration. The bit period is, let's say, 500 picosecond here, right? And so let's say, for example, I'm going from, I don't know, let's say 1.1 times I threshold to 2.1 times I threshold. Right, so I'm giving a pulse like that, and duration is 0.5 nanoseconds. So the power will go something like that. There'll be a rise time here, and then some oscillation, right? And then when I turn off again, like it'll be a turn off time, right? So if I look at now this frequency chirp, that will also follow something like this. So with a slight shift, but it sort of follows the pulse shape. So maybe I plot it on this side. So this is the frequency shift in gigahertz, let's say. Okay, so this is 0. So this corresponds to this, and then this dotted line corresponds to the right-hand side scale. Okay, so you can see basically as the optical power is rising, I have a positive, so near the leading edge of the pulse, this delta nu is positive, or a blue shift. Okay, and then near the trailing edge of the pulse, this decreases and even goes negative below 0, like a red shift near the trailing edge of the pulse. Okay, so if you look at sort of roughly the shape in the pulse here, it's like a negative slope. Right? So this delta nu versus time is a negative slope. So that's like a negative chirp. Okay. So basically, the effective chirp on the pulse goes like minus beta c. Okay. So the magnitude is proportional to the how large this beta c is, and the sign is of course negative because it's a negative chirp. Okay. So the typical C, so this C recall is in this convention where I'm right. So like if I approximate this like a Gaussian pulse, for example, remember I wrote the pulse like this. So let's say I have a Gaussian intensity profile, and then frequency chirp is included like that. Right. So this C chirp is, so if this C is negative, right, the instantaneous frequency decreases with increasing time in the pulse. And so basically, directly modulated laser diodes will always give you a negative chirp. Okay, the C value typically that you get for these DMLs are between, let's say, -6 to -2 in that range. Okay, so again, so now recall. So for example, we saw that if beta 2 C is greater than 0, which means beta 2 and C are of the same sign, right? So now I'm sending this through a fiber which has some UD coefficient beta 2. Then the pulse broadens. This is the worst case scenario, right? Fastest pulse broadening. So what you want is beta 2 and C to be the opposite signs, so that actually the pulse first compresses for a certain time and then, right? So again, recall beta 2 something like this. It crosses 0 at 1.3 micron, right? And then becomes negative. So D is opposite sign of beta 2. So D was negative below 1.3 and then became positive. Equivalently, beta 2 is positive below 1.3 micron and then becomes negative. So in the telecom range, 1.3 to 1.6, this beta 2 is negative for a standard single mode fiber. So, which is the bulk of the fiber laid down for our optical communication network. So basically for this fiber, right, you can see that a negative C is actually bad. Right. So again, for high data rate long haul links, we actually don't use direct current modulation. Again, because of this chirp factor also. Okay. Also, your data rates are limited, as we saw, below 10 gigabit per second. But also, it's worse than that because the dispersive effects will be even worse. Okay. So for these reasons, for high data rate long haul links, nowadays typically we exclusively use external modulation. But again, depending on the data rates you're operating and maybe for local area networks, the directly modulated lasers are still useful. Okay. Right. So maybe I'll stop here. So that's as far as sort of modulation of lasers is concerned. The next topic that we want to discuss is sort of noise. So intensity and phase noise in these lasers. But yeah, maybe we'll start that next time. It's a new topic. So any questions on what we discussed today? Either the small signal modulation, large signal modulation. I mean, of course, you can go into a lot more details about the operation of these lasers, which if you do maybe devices course or specific course on optoelectronics or something, you can go into. But for our purposes, for utilizing these in for telecom applications, sort of discuss the important points. Is it not the negative of the derivative of the phase? Yeah, I mean, I don't know. I guess this is in the convention. So either it doesn't matter if you take this plus or minus I phi of t. I mean, if you took plus or minus, I mean, this includes that. So basically, we are saying that this is like I of omega naught t plus phi of t. So the plus or minus is coming with both of them. Right. I hope that answers your question. So we don't need to take an extra negative sign. That's what you're talking about. Right. This phi of t is included with the omega naught t. I mean, if we wrote the phi as always like with a positive sign, and then it matters whether I take plus or minus omega naught t here, then accordingly I have to take the positive or negative derivative here. But in this case, we are defining the phase like this. So I hope it's clear that we don't need to take an extra negative. Right, so this is the phase acquired for the mode within the laser cavity, right? So it's like, so without this effect, like the laser is oscillating at some particular frequency, omega naught, and then this extra phase is added on because of the carrier.